Today, we're going on a hunt. We're looking for the roots of polynomials, those secret values hidden deep inside their equations. And our main tool isn't going to be a calculator. Nope, we're going to use a super powerful algebraic technique, polynomial division. Let's dive in. So check this out. Here's the graph of a polynomial. A graphing calculator is great. It can show us roughly where the curve crosses the x-axis. It spits out these, messy decimal approximations. But in the world of math, close just doesn't cut it, right? We want the exact values. So how on earth do we find them? Well, the answer isn't in a gadget, it's in the algebra. And to get there, we're actually going to rewind the clock a little bit. Way back, in fact. Because the key to solving this pretty complex algebraic puzzle is actually hiding in a skill we all picked up back in elementary school.
Does this look familiar? 49 divided by 4. It seems so simple, right? But believe it or not, the process, the step-by-step logic we all learned to solve this exact problem, that is the secret key to cracking our entire polynomial puzzle.
Let's just do a quick refresher. We ask, how many times does 4 go into 4? Well, that's easy. It's once. Then you multiply and you subtract. Then you bring down the next digit, the 9, and you just do it again. How many times does 4 go into 9? Twice. You multiply, subtract, and we're left with our remainder of 1. See? It's just a familiar rhythm.
And this is the big aha moment. Dividing polynomials isn't some brand new, terrifying concept. It's built on the exact same logic we just used. It's just taking that grade school algorithm and applying it to a slightly different kind of problem. I mean, look at this side by side. The parallel is absolutely perfect. With numbers, we focus on the first digit. With polynomials, we focus on the first term. In both cases, the game is the same. You match it, you subtract, and you bring down the next piece. It's the same dance, just with different partners.
And this really reveals the core strategy. It's all about being systematic. At every single step, your only goal is to make that leading, highest power term completely vanish. By knocking out the biggest term over and over again, we slowly chip away at the problem until it's much, much simpler.
Okay, now that we get the logic of long division, let's learn the pro-level shortcut. It's a super streamlined, much faster method called synthetic division. And it's perfect for dividing a polynomial by something simple, like x minus a number.
Here's how it works. First, the setup. We just write down the coefficients of our polynomial. And for the divisor, which is x minus 2, we use its root, a positive 2. The whole process is just a simple rhythm. Bring down the first number. Multiply by the root, add the column, and repeat. Multiply, add, until you run out of columns. That very last number on the end, that's our remainder.
But, and this is important, there is one major pitfall you absolutely have to watch out for. If your polynomial is missing a term, like say x cubed plus 8, which is missing the x squared and the plain x terms, you must use a 0 as a placeholder for each of those missing coefficients. I'm serious, if you forget this, the whole process just falls apart and your answer will be totally wrong.
So, we've pretty much mastered the mechanics. But this isn't just about crunching numbers and following steps. That final value we calculate, the remainder, it actually holds a really powerful secret about the polynomial itself.
So let's ask the critical question. We go through all this work just to find this one little number at the end. What is it really telling us about the big polynomial we started with?
This, my friends, is the remainder theorem, and it's an incredible shortcut. It says that the remainder you get from dividing by x minus c is the exact same value you'd get if you just plugged c into the polynomial in the first place. So yeah, all that division work was just to get a number you could have found with simple substitution. Now, why is that useful? Well,
that leads to the big payoff, the factor theorem. This is what connects everything. It says c is a root only if x minus c is a factor. And think about it. If c is a root, what's the value of the polynomial at c? It has to be 0, which means the remainder must be 0. Getting a remainder of 0 is the jackpot. It's mathematical proof that you found both a root and a factor.
All right, now we have all the tools we need. We get the logic of division, we have a fast shortcut, and now we know what the remainder actually means. It's time to go back and solve that puzzle we started with. So here's our original graph again. Looking closely, it really seems to cross the x-axis perfectly at x equals 2. Thanks to our new friend the factory theorem, we now know this isn't just a guess, it's a powerful clue.
If x equals 2 is a 0, then x minus 2 must be a factor of our polynomial.
So let's test that theory. We use synthetic division with our root, 2. We set up the coefficients, bring down the 1, multiply and add again, and, would you look at that, a remainder of 0. Our guess was correct. X minus 2 is officially a factor.
So what did we just do? We took that messy cubic polynomial and we broke it down into two simpler pieces. We have the factor we knew, x minus 2, and then we have the part that was left over, a much, much friendlier quadratic equation.
Now the problem's way easier. We know one root is 2. To find the others, all we have to do is solve the remaining quadratic piece. And okay, it doesn't factor nicely, but that's no problem at all. We can just use the good old quadratic formula. We plug in our a, b, and c, and we get our final answers.
And here they are, the three exact roots of our polynomial. We have x equals 2, x equals -3 plus the square root of 2, and x equals -3 minus the square root of 2. And if you punch those into a calculator, you'll see they perfectly match those decimal approximations we saw in the very first slide. We found them!
And this, right here, this is the key idea that ties it all together. A 0, a factor, and an x-intercept. They are all just different ways of looking at the very same thing. If you find one, you've pretty much found them all. Really internalizing that connection is the true secret to mastering polynomials.
So, we've figured out how to find the exact points where a polynomial crosses the x-axis. But what about a graph that never touches that line at all? Does that just mean it has no roots? Not exactly. It just means its other roots are hiding, in a place we haven't looked yet, a completely different kind of number. But that is a story for another explainer.